Hello, this is the audio and video for Lecture 16. In this video, we're going to start Chapter 13, which is on vibrations and waves. The first thing we're going to do is talk about springs. So let me draw your attention to the right side, the middle picture in particular. This picture shows an object attached to a spring. The object is just sitting there. The spring is not stretched. It's not compressed at all. The whole system is just sitting motionless. We call this equilibrium. In the top picture, the object is displaced a distance x to the right of that equilibrium position. Now imagine you do this in real life. You pull an object to the right, the spring is going to try to pull back to the left. Okay, the force that the spring is exerting on the object is represented by this variable Fs. Now in the bottom picture, the object is displaced to the left by a distance x, and the spring is trying to exert a force to the right, also represented by the variable Fs. Now Hooke's law says that the force that the spring exerts on the object is equal to minus kx. K is something we call the spring constant. K is a number that represents how strong the spring is, and x is that distance that the object is from equilibrium. The setup for this question is that you have an object attached to a spring, you pull the object to the right, and you let it go. The spring then causes the object to move back and forth. As the object's moving, it has a position, it has a velocity, and of course it also has an acceleration. So, what is the acceleration of the object as it moves back and forth? Now we don't have a lot to go on at this point, but I still want you to pause the video, think about the question, and see what you can come up with. Unpause the video when you're ready. Okay, so what little we do know so far is that as the object moves back and forth, the spring is exerting a force on that object. We know that force is given by Hooke's law as minus k times x. We also know that Newton's laws are basically always true, so F is equal to ma, and since the spring force is a force, we can set those two equal to each other. This brings us to the middle equation, which says that the mass of the object times the acceleration of the object is equal to minus the spring constant times the position of the object. If we solve for A, we get the equation on the right side, which is the answer to the question. Notice that in this equation, the acceleration is not constant because acceleration depends on x. As the object moves back and forth, obviously the position is changing, so that tells us that the acceleration the object feels is also changing. Note that this is very different than acceleration in the context of, say, gravity, where an object falls to Earth at a constant acceleration of negative 9.8 meters per second squared. This tells us that spring motion is going to be very different from gravitational motion in terms of the equations that we're going to be using to describe it. Also in this equation, notice that when the object is pulled furthest to the right or pushed furthest to the left, at these points the x value is the largest, so the acceleration is also going to be the largest. And finally, when the object is dead center in that equilibrium position, at that point x is equal to 0, so the acceleration that the object feels is also 0. On this slide, let me first point out that when the object is displaced to the right of equilibrium, as in the top picture, then we say the position is positive, so that x is greater than 0. And in the bottom picture, when we displace the object to the left of equilibrium, we say the position is negative, so x is less than 0. Also, let me point out that the spring constant k is always a positive number. So k is always greater than 0. Now, Hooke's law says that Fs is equal to minus k times x. So in the top picture, when x is positive, we have a positive number times k, which is a positive number, times a negative sign. that tells us that the right side of this equation here, this is a negative number. So if the right side's negative, the left side also has to be negative. Since F is equal to ma, if the force is negative, then the acceleration is also negative. So if the object is to the right of equilibrium, the force and the acceleration are going to be to the left. Now the second bullet point here is just the opposite of the first. So hopefully you followed along and you can work that out for yourself. But the gist of it is that when the object is to the left of equilibrium, both the force and the acceleration are to the right. And the third bullet point says that when the object is crossing over that equilibrium position, then x is equal to 0, so both the force and the acceleration are 0. The note at the bottom, this is something similar to what we were doing in the electricity section. It just says that rather than saying that the force is equal to minus k times x, sometimes it's easier to say that the absolute value of the force is equal to k times the absolute value of x. Right? Just take the absolute value of everything, don't worry about whether anything is positive or negative, and then just figure out which direction the force points after the fact. This slide is mostly just definitions, so I'll let you read through those, but let me point out that amplitude has dimensions of length. So typically we would say that amplitude is measured in either meters or centimeters, and period has dimensions of time. So period has units of seconds. And then at the very bottom, just to say it out loud, the units of frequency are hertz. And 1 hertz is equal to 1 times 1 over seconds. We can write the period of the object in terms of the mass of the object and the spring constant via the equation on the left here. And then the equation for frequency comes from that relationship on the previous slide that said that F was equal to 1 over the period. In the middle, we define this new variable called angular frequency. This symbol is the small Greek letter omega. So we say that omega is defined as the square root of k over m. Now we call this angular because there's some relationship to circular motion. I don't intend to spend too much time on this, but if you want to know the details, you can look in section 13.3. The units of omega are also hertz, but sometimes we say that the units are, so instead of hertz, which is 1 per second, sometimes we say that omega has units of radians per second. And we say that because of the relationship with circular motion. Okay, then the equations at the bottom you can derive from the other equations on this slide. Here's a question. I will let you read through it and then pause the video to think about it. Okay, so on the previous slide we saw that the period can be written as 2 pi times the square root of m over k. So we might say that the initial period is equal to 2 pi times the square root of m0 over k. And then after we double the mass, we have a new period, which we would write as 2 pi times the square root of 2 times the initial mass divided by k. This 2 I'm going to pull out of the square root, so I'm going to write it as the square root of 2 times 2 pi, the square root of m0 over k. And then this term that I'm circling, this is equal to the initial period, so I can write this as the square root of 2 times the initial period. Okay, so the square root of 2 is approximately 1.4. T0 is 2 seconds. 1.4 times 2 is 2.8. So the answer here is D. This question is very similar to the previous question, but here we are doubling the amplitude of oscillation and we're leaving the mass of the object alone. So let's first think about what the question is asking. Let's say that I set the equilibrium position to be at the center here. And now if I pull back the object so that it has an amplitude here, the amplitude would be this distance here. If I pull it back to there and I release it, the spring will cause the object to oscillate like this. Now if I double that amplitude and I pull the object back to here, when I release it, the spring will cause the object to oscillate like this. Okay, now the question is asking, how does the period for this larger oscillation compare to the period for the smaller oscillation? Go ahead and pause the video and think about it for a minute and unpause it when you are done. Okay, so we know that t is equal to 2 pi times the square root of m over k. K is a constant, it's the spring constant, so it's constant for every spring. And in this problem, the mass is also constant. So what's interesting is on the right side, I'm multiplying a bunch of constants together. This tells me that the left side will also be constant. So if t starts at 2 seconds, t will stay at 2 seconds. Now this might seem counterintuitive, because maybe you're thinking in the smaller oscillation, the object has less distance to travel, so it should be happening faster. What's interesting is that for this type of motion, period actually does not depend on amplitude. Now the short of it is that if you have a larger amplitude, so when you pull the object back further, you actually start with a stronger force, because Hooke's law tells us that the force is related to how far you pull back the object. And then if you have a larger force, you have a larger acceleration because of Newton's second law. And then a larger acceleration will result in a larger speed. So that larger speed compensates for the larger distance that the object has to travel in the larger oscillation. I'll let you read through this question, but my hint for it is that we haven't seen any equations so far that have velocity in them, so rather than trying to find an equation to help you answer the question, think about what's happening with the object as it moves back and forth. Okay, so let's say that the object is moving to the right. As it gets close to that furthest right point, it has to slow down before it can move to the left. Right? And then as it starts to move left, it speeds up to the left. When it gets to that furthest right point, it has to very briefly stop. So the velocity will be 0 at that point. This is similar to when you throw an object into the air, and as it gets to the very highest point, it has to stop before it can come back down. It's the same thing that's happening here. Now similarly, when the object is moving back left, as it gets to that furthest left point, it has to slow down so that it can turn around and start moving right again. So at that furthest left point, the velocity will also be 0. So then the answer here is B. The setup for this question is the same as the last question, but the question is actually asking about the magnitude of acceleration rather than the velocity. Here you might find it easier to look for an equation to help you out. Okay, the equation that I was thinking of was from a few slides ago. We saw that ma was equal to minus k times x, or I guess even better, a is equal to minus k over m times x. Now a will be largest when x is largest. and x is largest at the amplitude points. Since it's only asking for magnitude, we can ignore this minus sign here, and the acceleration will be largest then at the amplitude positions. This is the last question in this series of questions. So what is happening with the block when it's at the position shown in the picture? Go ahead and pause it to think about it. So the answer is that we don't know, because we don't know which direction the block is currently traveling in. If, for instance, the block was traveling to the left, then we know it's approaching that leftmost amplitude point, so it has to be slowing down so that it can turn around. If instead the block was traveling to the right, then the block is still speeding up from when it had previously reached that left amplitude point. So the answer here is going to be C. This question is asking you to summarize what you learned in the 3 previous questions. See what you can come up with. Okay, I'm just going to put the answers on the slide and let you read through them. The motion described on the previous slide is called simple harmonic motion. Sometimes we'll call it simple harmonic oscillation, so we abbreviate it to SHO. Now, any system undergoing simple harmonic motion is called a simple harmonic oscillator. More generally, any system that obeys Hooke's law is a simple harmonic oscillator. There's 2 important parts to this. The first is that the force is proportional to the displacement of the object. We know this is true for a spring because F is equal to minus K times X. The second is that F is a restoring force, and we saw that this is also true for a spring. So far we've only talked about horizontal springs, but it's also true that vertical springs are simple harmonic oscillators, and we'll see some of those in examples in the future. And we'll also see that pendulums are simple harmonic oscillators. All objects undergoing simple harmonic motion share these features. First is that the acceleration of the object is 0 as the object passes over the equilibrium position. So in the middle picture, we can write A is equal to 0. This is true because we require that F is proportional to the position of the object. So if X is equal to 0, then both the force and the acceleration will be 0. Next is that the acceleration is largest at the amplitude positions. So then in the 1st and 5th diagram, we can draw large acceleration arrows, like so. Then in the 2nd and 4th diagrams, we can draw smaller acceleration arrows. So the acceleration in the top picture is largest and to the left, then it decreases in the 2nd picture, it becomes 0 in the 3rd picture. In the 4th, it's small and pointing to the right, and then in the last picture, it's largest and pointing to the right. Something similar happens for velocity, but in a way it's kind of the opposite. V is 0 at the amplitude positions because the object needs to turn around, and then at the center, that's when the object is moving the fastest. The arrows for velocity are already drawn in green. In this example, we start by hanging a spring from the ceiling. We then attach a ball to the bottom of the spring and we let it come to rest. So the ball and the spring are not moving at all. The whole system is in equilibrium. Okay, now this is kind of a tricky problem, so I'm going to let you read through it and think about it. But keep in mind that we covered similar ideas in the electricity section. Remember, we were suspending a little oil droplet inside of an electric field. The idea is very similar here. So pause the video and unpause it when you're ready. We already have a force diagram drawn for us on the right side of the slide. So let's look at that to see how the forces are balancing each other out. We have gravity pulling down on the ball with a force of mg, and we have the spring pulling up on the ball with a force of Fs. Now, since the object is at rest in equilibrium, the acceleration of the object has to be 0. So let's look at Newton's second law that says that ma is equal to the net force on the object. Since a is 0, we can set the left side equal to 0, and then the net force is going to be the sum of the two forces. So you have the spring force pointing upward, so that is going to be positive. Gravity is pointing downward, so I use a minus sign for that. And notice here I've used this idea where instead of dealing with minus signs for the forces, I've just taken the absolute value of the spring force as well as gravity. This way I don't have to worry about that extra minus sign tripping me up. Okay, then I plug in Hooke's law for the spring force. I get k times the absolute value of x. And for gravity, I just use m times g. The question is asking us to find the spring constant, so I can now just solve this equation for k. I find k is equal to mg over x, which should technically have these absolute value bars around it. And then I just plug in the numbers and I'll find that the spring constant is equal to 270 newtons per meter. I don't really think we'll use the ideas from this example very much, but I thought it was interesting to compare it to what we learned in the circuit section. So in this problem you have two springs connected to one ball, and the two springs are connected in parallel to each other. And the question asks, what is the effective spring constant of the system? So if you were to replace those two springs with one single spring, what would be k for that single spring? Let's start by drawing a free body diagram for the ball. You have gravity pulling downward with a force of mg, and then you have two spring forces pulling upward. The first we'll label Fs1, and the second we'll call Fs2. Okay, now if you were to balance these forces and use Newton's second law, you would find that 0 is equal to Fs1 plus Fs2 minus Fg. Then plugging in Hooke's law and mg for gravity, you'll find the equation on the right-hand side. Now the springs are connected together to the ball, so the position of the ball is going to be the same for both springs. Basically what I'm saying is that this x is the same as this x. Now since that is true, we can factor out that x, and we'll end up with k1 plus k2 times x minus mg. This k1 plus k2, I'm just going to call the effective spring constant, as if it were one spring. So what we see is that if you connect two springs in parallel, that their spring constants add together. Similarly, you can show that if you have two springs connected in series, the relationship at the bottom holds. This is actually opposite what we found for resistors. When you have two resistors in series, you just add the resistances. But I still thought it was interesting that you can find similar behavior in springs. So now we're going to move on to section 13.2 and start talking about potential energy. For a spring, we call it elastic potential energy. So imagine you have a mass oscillating on a spring. This mass has some kinetic energy, and it also has some potential energy. Now we know that gravitational motion can't really compare to spring motion, but I still want to draw a parallel to help you drive your intuition. So when we have a ball falling through the air, the kinetic energy of that ball comes from the actual motion, the actual falling of the ball. In comparison with the spring, I want to say that the kinetic energy comes from the oscillation, from the actual motion of the spring, or the motion of the object connected to the spring. When we're talking about a ball falling, the potential energy of the ball comes from the height of the ball above the ground. The height of the ball is the position of the ball. Now when we look at a spring, the position is related to how stretched or how compressed the spring is. So the potential energy for a spring will be related to the length that the spring is stretched. Now, as the spring oscillates, it does work to convert energy between kinetic and potential energy. So when the object is moving the fastest, it will have the largest kinetic energy. This happens as the object passes the equilibrium position, as we saw a few slides ago. When the spring is compressed or stretched the most, this is when it has the largest position, right? When it's at the amplitude points. At these points, it will have the largest potential energy. So all of the potential energy that it has at the amplitude points has the potential to be converted to kinetic energy at the equilibrium position. Okay, this is a quick question to test whether or not you were paying attention on the last slide. So I will let you pause the video, read through the question, and then unpause when you're ready. The answer here is going to be D. The explanation for that are the last few bullet points from the previous slide. Basically, the object is moving fastest in equilibrium, or as it's passing the equilibrium position. So the kinetic energy will be at a maximum value. And then the position, the x value, is largest at the amplitude positions, so the potential energy will be largest at the amplitudes. The kinetic energy for an object attached to a spring is the same energy of motion that you know and love. It's 1/2 mv squared. For potential energy, we use this equation in the middle of the slide here. I won't derive it, but it's just that the potential energy is 1/2 kx squared. I do want to note that the potential energy is largest when x is the largest, and when x is 0 in equilibrium, the potential energy is also 0. And the final bullet point down here is just another statement of conservation of energy. If you add together the mechanical and the potential energy, you get the total energy, and this is always constant. On this slide, we have to do a little math. So in the first line, I write that the total mechanical energy is equal to the kinetic plus the potential, and then I substitute in the 1/2 mv squared and the 1/2 kx squared. Now, this equation is true at all points of the oscillation. But for the next two bullet points, I want to look at two specific points of the oscillation. First, I want to look at the amplitude position. So at this position, x is equal to a, and we know that the velocity is equal to 0 because this is where the object is turning around. Now I want to write the total mechanical energy equation at this amplitude position. So I have E is equal to the potential energy plus the kinetic energy. But since the velocity is 0, the kinetic energy will be 0, so I ignore that term. So at the amplitude position, the total mechanical energy is equal to 1/2 times Ka squared. I want to do something similar at the equilibrium position when x is equal to 0. At this point, we also know that the object is moving at its fastest velocity, so I can say that the velocity is equal to Vmax. So again, I want to write the total mechanical energy equation. E is equal to the kinetic energy plus the potential energy, but since the potential is 0 at the equilibrium position, I can ignore that term. So at the amplitude position, I find that the total energy is equal to 1/2 Ka squared. At the equilibrium position, I find that the total energy is equal to 1/2 times mv max squared. Now the total energy is always constant, so the total energy at the amplitude position should equal the total energy at the equilibrium position. That gives us the equation on the lower left. Now we can actually simplify this equation a little bit. I will let you work out the details, but remember that omega is equal to the square root of K over m. So if you simplify it, you end up with this actually very nice equation that relates the maximum velocity to the amplitude of the object. This is a quick question, so take a look at it, think about it, and then unpause the video when you're ready to see the answer. So this is an application of that last equation we saw on the previous slide. You have that the maximum velocity is equal to omega times a, and if you break down omega, you have that it is equal to the square root of K over m. Notice that K is a constant and m is also a constant. So omega for this problem is constant. Then in the problem it asks us to double the amplitude. So if a goes to 2a, this tells us that Vmax should go to 2 times Vmax. Right. If the right side of the equation doubles, then the left side of the equation has to double to compensate. So if the maximum speed starts at 8 meters per second, then the final answer should be D, 16 meters per second. This is a fairly complicated example, so read through it carefully, think about it, and then continue when you're ready. If you try to do this problem with forces and Newton's laws, you're going to give yourself a headache. But if you use conservation of energy, it's actually very straightforward. So the initial energy, the initial total mechanical energy comes from kinetic and potential. But notice that the car starts at rest. This means that the initial kinetic energy is 0. When the car gets all the way to the bottom and it compresses the spring, when the spring is compressed at its maximum, that means the car is stopped. Right? That's essentially when the spring is turning around. So the object, the velocity of the object is 0. So then the final kinetic energy is also going to be 0. So then this conservation of energy equation, EI is equal to EF, that's going to turn into the initial potential energy is equal to the final potential energy. The initial potential energy comes entirely from gravity. So you use the gravitational potential energy equation, m times g times h. The final potential energy comes from the spring. So for that, you use the elastic potential energy equation, which is 1/2 k times x squared. Since those two have to equal each other, we have this equation near the bottom. And then the car asks us for the maximum distance the spring is compressed and that value is represented by the variable x. So to finish the problem, we solve for x, and then you can just plug in all your numbers, and hopefully you find that the spring is compressed by 0.51 meters. This slide is another quick derivation, but if you were following along on slide 22, then this is essentially the same thing. The very first equation we have here is the total mechanical energy equation, and then the middle equation was the equation we found at the amplitude position. So now remember, the total energy is conserved, so this value of E has to be equal to this value of E. So then you can write that 1/2 mv squared plus 1/2 kx squared is equal to 1/2 k times a squared. So if you take this equation and you solve for velocity, you'll end up with the equation on the right. The equation on the right can be a useful equation, and so that's why we derive it. Notice that at some point you do have to take a square root, and when you take a square root, the answer should end up with a plus or minus sign. Just thinking about the situation, we know that when an object is moving to the right, it should have a positive velocity. So in that case, we would take the plus sign, and if the object is moving left, it should have a negative velocity, so we'll use the minus sign. Now, since we didn't run the full derivation of it, well, hopefully you do it at home, but since we didn't do it here, we can still check to see if it meets our expectations. So let's plug in values at the amplitudes. At the amplitudes, when x is equal to a, let's use the rightmost amplitude point, we would have v is equal to plus or minus omega times the square root of a squared minus a squared, and this is equal to 0. So at the rightmost amplitude point, the velocity is equal to 0 as expected. At the equilibrium point, you have x is equal to 0. So then you have v is equal to plus or minus omega times the square root of a squared minus 0 squared. The 0 goes away, you get plus or minus omega times the square root of a squared, which is just plus or minus omega times a. So at the equilibrium position, you have v is equal to plus or minus omega times a. This is exactly what we expect. In fact, at this position, we know that v is also equal to v max. So far, we've only looked at the objects at specific points of the oscillation. Specifically, we've been looking at the amplitude positions and the equilibrium position. But the object moves continuously along the entire oscillation. Right? So the position, the velocity, and the acceleration are changing during this entire oscillation. I'm not going to derive these specific equations. If you're interested in the details, they're in sections 13.3 and 13.4. And we will look at this sinusoidal motion more in the next lecture. But for now, I just wanted to show you these three equations: the x as a function of time, the v as a function of time, and the a as a function of time. Now quickly, let's look at the graphs just to see if they match with our expectations. So the top graph represents the actual position of the object, this x variable here. So the object starts at an amplitude point, and then the object moves toward the equilibrium point, and then toward the other amplitude point. Comparing with velocity, we know that at the amplitude point, the velocity should be 0, which it is. We know that when the object gets to the equilibrium position, this is when the object should have its maximum velocity. And in this case, it does have its maximum velocity, but it is negative, the maximum velocity. And then third, when the object gets to the second amplitude position, the left amplitude, the object again has 0 velocity. Now if we keep going down for acceleration, at the amplitude position, the acceleration is at its maximum value, but also this value is the negative of the max. At the equilibrium position, the acceleration is 0, and then at the second amplitude point, the object has its maximum acceleration, and this time positive. Now, this question was in the slides that I posted last week, so I kept it in this lecture so I could mention it, but I think the question is poorly formulated, so let's pretend like this was never in the slides to begin with, and instead, let's pretend like it was replaced with this question. So take a look at it, look at the equations on the previous slide, and unpause when you're ready to hear the answers. For maximum velocity, we use the equation Vmax is equal to omega times a, and omega we're going to write as the square root of k over m. So now in the question we have a mass and we double it. So that means Vmax, which is equal to the square root of k over m times a, is going to go to the square root of k over 2m times a. The 2 I want to factor out, so I get 1 over the square root 2 times the square root of k over m times a. Now this k over m square root times a is what I started with for Vmax. So Vmax goes to 1 over the square root of 2 times Vmax. Okay, so none of these are any of the answers listed, so for the maximum velocity, the answer is D. For maximum acceleration, I'm going to use the equation Amax is equal to omega squared times A from the previous slide. Here, omega squared is going to be just k over m, and then that's times A. Now if m goes to 2m, then A max equals k over m times A goes to k over 2m times A, which I factor out the 1/2 and I get 1/2 times k over m times A, which is 1/2 the same Amax that I started with. So if the mass is doubled, then the acceleration is cut in half. So the answer for acceleration is A. This question uses ideas that we have already used a couple times this lecture, so I'm going to leave this one to you guys. I will flash the answer so you'll know if you get it right or wrong, but I won't go over the answers, And if you have any questions, please just let me know. So here are the answers. And now in section 13.5, we're going to show that the motion of a pendulum behaves according to simple harmonic motion. Now, if you don't follow the exact details of this slide, that's okay. You don't need to know the details to continue on, but see if you can follow along. So let's start by looking at the pendulum on the right side of the screen. You have a mass hanging from a rope, which is attached to the ceiling. The mass, there are two forces acting on the mass. You have the tension in the rope that's pulling the mass upward, and then you have the force of gravity that's pulling the mass downward. Now, the force of gravity we can break into two components. The first component is the component of gravity that's pointing the opposite direction of the tension force, and the second component of gravity is the component that's perpendicular to the tension force. Now, the component that is parallel to the tension force, the one on the right, this one does nothing for the motion of the pendulum. The force of gravity that's perpendicular to the tension force, that's the component that's actually causing the pendulum to swing back and forth. So the perpendicular component of the force minus mg sine theta, this is the force that's actually causing the motion. Now, I promised you that we were going to see that pendulums behave according to simple harmonic motion, but if you look at this equation, you can see that it doesn't actually fit our definition of simple harmonic motion. The requirement in particular that doesn't fit is that the force is not proportional to the position. The force here being F perpendicular. This is not perpendicular to the position, which in this case would be theta. F is in fact proportional to the sine of theta. So the motion of a pendulum in general is not simple harmonic motion. However, for small angles of oscillation, we can actually approximate the restoring force as minus mg theta. So in a little more detail, if theta is small, then we say that the sine of theta is approximately equal to theta. And then in that case, we would say that F perpendicular is approximately equal to m times g times theta. Now, this equation does show that F perpendicular is proportional to theta. So the force is proportional to the position. So this does, in fact, fit our definition for simple harmonic motion. And then the final thing we want to do on this slide actually involves a little geometry. Rather than using the angle theta in the picture on the right, I actually want to use S as our position variable. And S here is the arc length from the center to where the object is. So using a little geometry, I can show that the restoring force is equal to minus mg divided by L times S. So the mass of the object times the gravitational constant divided by the length of the string times the arc length. So for small angle oscillation of a pendulum, we have that the force is equal to minus mg over L times S. And if you compare this with Hooke's law, you'll see that this mg over L, this is supposed to be our K. This is our spring constant. And then S is the displacement from straight down. Again, that's the arc length. Now this fits the bill for simple harmonic motion. That means all the analysis we did in the first 29 slides, that applies to pendulums as well as springs. Here I picked out a couple examples. You can write the angular frequency of pendulum oscillation as the square root of g over L. You can write the period of oscillation. You have the acceleration at time t given by the same acceleration formula. And I do actually also want to point out that the period in this case is again independent of amplitude. This t here, it only depends on the length of the pendulum and it depends on the gravitational constant. But for a pendulum, if you lift it a little bit higher, it's going to take just as long to swing back and forth than if you just tap it. This slide is just to show you the comparison between the two types of motion. So if you start in figure A, you have the pendulum pulled all the way to the right. The mass attached to the spring is pulled all the way to the right. You let the pendulum go, and the pendulum starts to swing down. When the pendulum reaches the middle position, that's the equilibrium position, that's when the box would also reach the equilibrium position. The pendulum then continues to swing left. As the pendulum gets to its leftmost position, the amplitude position on the left, that's when the box reaches the amplitude position on the left. Okay, and then that motion continues in reverse for D, E, and F. So this is actually not a great comparison because you can actually see them in motion moving together. But if you at least take a look at page 461 in your book, you can see a better image of this. And here's our last question for this lecture. Basically, the setup is that you have 4 different pendulums. They are all swinging with the same small angle amplitude, so they're all exhibiting simple harmonic motion, and they all have the same amplitude, but the length of the strings are different and the masses attached to the strings are different. So the question is, what are the correct rankings for the frequencies of the pendulum, starting at the largest and going to the smallest? This question takes a few pieces to fit together. So take your time, think about it, and unpause when you're ready to hear the answer. So 2 slides ago, we saw that the period of oscillation for a pendulum is equal to 2 pi times the square root of L over G. And back from near the beginning of the lecture, we saw that frequency was 1 over the period. This is also going to be true for the pendulums. So if we take 1 over the period that we have written above, we will get 1 over 2 pi times the square root of G over L. So the frequencies for the pendulum depend on 2 things: G, which is a constant, and L, the length of the pendulum. So if we want to rank the frequencies, all we have to do is look at the length of the pendulums. It's the only thing on the right side of that equation that's not constant. Now, since F is proportional to 1 over the square root of L, the longer the pendulum, the shorter the frequency. L in the denominator, so a large L, will lead to a small f. The longest pendulum is C, so C will have the smallest frequency. After that, we have pendulums B and D. They have the second longest lengths, and they're equal, so the frequencies for pendulum B and D will be equal to each other. And A has the shortest length pendulum, so it will have the longest frequency. So that's the answer, and I wrote it backwards, but that corresponds to answer A. Now, these last two slides were meant to be questions for discussion. Obviously, we're going to handle discussion a little differently than we've been doing. I'm not sure how we're going to do that yet, but for now, I'm going to just leave these questions for you to do. If you have any questions, of course, please let me know, and I will show you the answers so you know if you do them correctly. This first question is a short derivation. It's just a few lines. So here's the answer. And then this next example from the book is a little more complicated, but again, I will leave it for you to do. And if you have any questions, please let me know. And here are the answers. So hopefully the lecture went okay on your end. If you're confused about any of the material in the lecture, please go back and watch the video again or look in the textbook. And of course, you can contact me at any time. Have a good day.